going to talk about one solution of Fourier summation using fixed point accumulator. The Fourier summation is algorithm for summing floating point numbers with reduced rounding errors. One solution of the Fourier summation problem is presented by using fixed point accumulators. It is well known that the summation of large sets of numbers can be very inaccurate due to the accumulation of rounding errors. So far, several authors have used variety of methods for floating point summation to find out which methods achieve the best accuracy. The first algorithm solving a Fourier summation problem was Kahan's method. Kahan's compensating summation method employs the correction on every step of summation. Correction for rounding errors is also computed and saved, and it is also added to term in next iteration cycle. Problem with Kahan's method is that correction will be lost if term in next iteration is relatively large to correction, and that is then we see the usage of Kahan's Babushka-Klein summation algorithm, because it tries to overcome shortcomings of Kahan's by recursive correction. This algorithm needs a whole array of terms and also needs a large amount of memory to save data between recursions. The best algorithm is the method of cascading accumulators. It uses an array of 64 double precision floating point accumulators. Every single precision term with 4 consecutive exponent values is accumulated to appropriate cascading accumulator. The method of cascading accumulators is proved to be the best in performance and precision. Fixed point accumulator is a 320-bit multiple precision integer, which is implemented as array of 5 64-bit integers. The compiler puts these numbers into registers, so the numbers are not stored in cache memory, and therefore this solution is potentially faster than another ones. Also, floating point numbers which are accumulated do not need to be promoted to the whole fixed point type and then to be added to fixed point accumulator. Instead, an optimized approach is used. So in this graph, we can see that if a floating point number is denormalized, then mantissa would be accumulated to accumulator to the lowest part of accumulator 0, and then carry will propagate it from accumulator 0 to 4th accumulator. And on the other hand, if floating point numbers are normalized, we would have exponent would be shifted before mantissa, and we also have local and global shift. Local shift mantissa, local shift. Local shift will be used for mantissa, and after that, global shift will decide which accumulator number will be added temporal accumulator, and carry will be propagated from accumulator n plus 1, and up to accumulator 4. The advantage of the shown solution in comparison to the method of cascading accumulators is that it has up to 12 times less memory used. Fixed point accumulator need 40 bytes, while cascading accumulator needs 512 bytes. There are three problems: many smalls, one large, many smalls, and one large, many smalls, many tinies. Fixed point accumulator, fixed point algorithm is compared with Kahan's method, which is a classic algorithm, and the method of cascading accumulator, which presents the best solution due to its performance and precision. Many smalls, one large is problem where many small numbers are being summed with one large number. Also, one large, many smalls is problem where one number is being summed with many smaller numbers. One large, many smalls, many tinies is a problem where one number is being summed with 2 on 24 small numbers and 2 on 26 tiny numbers. So here we have a table in which there are two numbers are shown for each method and problem. First represent obtained value of algorithm, and the second one presents the time required for execution of problem in 1,000 iterations. So we can see that Kahan's algorithm does not work for problem one large, many smalls, many tinies, because correction variable is bigger than is larger or equal than small number in the moment when tiny numbers are started to be accumulated, and tiny numbers will be lost because they are order of epsilon of small number. To solve this Kahan's problem, we need a correction variable for compensation variable for correction variable, and for that we use Kahan-Babushka claim algorithm. And I also have to mention the bad side of cascade accumulator method. Bad side is that it requires double precision floating point accumulators, and they are not always available. So if we need a cascade accumulator method for double precision, in some ways it couldn't be implemented. On the other hand, fixed point accumulator works on any architecture. And also, fixed point accumulator is better on hardware due to the fact that it occupies less logic and work better than floating point units on hardware. It has been proven that the accurate summation using fixed point accumulator algorithm does not have rounding errors, as well as the method of cascading accumulator, which is the best algorithm due to its precision. And it is shown that solution presented in this paper has comparable performance as cascading accumulator method. Future improvement in C++ can be achieved by optimizing solution in assembler and implementing double precision version. Also, hardware implementation should be implemented and compared to other algorithms. And this solution should also be compared to more algorithms and problems.
Questions?
Can you please help us understand these numbers from the table one and versions? What hardware did you use to actually execute this experiment?
Can you repeat?
What hardware is used to execute this at flash?
We only did it on processor.
What kind of processor? Personal computer?
Personal computer. Our future plans is to do this on FPGA.
Yeah, it feels like really slow for 100 iterations to actually be close to 1 minute execution.
It is only 2 times slower than cascading accumulator. It would have better performances in hardware or, for example, in FPGA.
Sure. So this is just a simulating results and looking at the precision level and comparing these performance criteria on the same hardware to just
we just want to see results and to compare
the performance.
Yes.
Okay.
Can you explain the effect of many smalls, one large, and one large, many smalls and problems? Is it because we have this iterative algorithm that it matters? I mean, what the first 2 scenarios?
What is the
What's the difference between the first 2 scenarios? Because I'm a bit distant to the field. Yeah?
Can I explain on an example?
Yeah, sure.
If you have one large number, think about 1.
Yeah,
and you add 10,000 of small numbers.
You add numbers to it.
Yeah.
Iteratively. So the carry is okay, carry is carried along, yeah, so it doesn't matter. But the large number comes after the small ones, then it's a problem, right?
It is a problem, right?
But
some of many smalls, one large will be 2, but one large, many smalls will be 1. Because,
it's a general problem with the floating point algorithm. So you cannot really do a proper summation of large and small numbers because you need to have a really wide mantissa, like you pointed out, 512, to actually get a whole range of numbers. So that's now meaningless to apply the floating point.
Okay, and another one. How do you implement one large, many small, many tiny? I mean, how do you actually implement these large and small? What is the quantitative way of?
We said that large number is, for example, 1, while small number is 2 on 24. Tiny number is 2 on 26.
Okay, so you have these quantified, like some standardized way of calling it tiny, yeah, and small.
Yes.
Okay. And the other one, sorry, how do you measure the memory consumption? Because you said that comparing to the cascade accumulator, your algorithm is better, I mean slower on one hand, but better in the sense that it doesn't take up as much.
The cascading accumulator method uses cache memory.
So you don't.
And it is also beneficial and is scalar or
But do you have a way of also looking at it, or?
We use less memory because we put these numbers into registers, not into cache memory.
Okay, that's the difference. So, okay, thank you very much.
One more question. Can you give me an example of a small number and an example of tiny?
Small number is 2 on 24 and tiny is 2 on 26. How?
Minus 24. Minus 24.
Okay. Okay, thank you.